All right, up next we'll have Andrew Soignet. He's going to be talking to us about gas turbine electrical generation, which is lead for next week experiment. I believe experiment 5, right? Experiment 5.
I think 4.
4.
I'm not sure.
4 lead, yeah.
Hi, my name is Andrew. I'm the lead for the gas turbine electrical generation experiment, and I'm telling you about it today. All right, so first up, we have some goals of the experiment. The first goal is really just to get an understanding of what's going on, how gas turbines can be used to generate electricity. Gas turbines are not really as prevalent as steam turbines because they're not nearly as efficient, but a lot of large plants have them on hand in case they need a little extra production or whatnot. So with the apparatus, we're going to collect a lot of data. As you'll see, this device has many probes and temperature sensors built in. It can pretty much get whatever we need. And then lastly, we're going to use all this to get a lot of quantities that can be used to evaluate system performance or performance of individual components of the entire assembly. All right, so on the left here, we have a picture of the apparatus. The silver part on the left is the jet engine, and on the right is the electrical power component. We have a computer to collect data, and then a control panel. But really, what we need to pay attention to here is the schematic on the right. It breaks everything down. So basically, we have ambient air come in to the intake. The pressure is brought up through a compressor. Then enters a combustor where it's burned. And lastly, it's expanded through a turbine. These three components, the compressor, combustion chamber, and the turbine, make up the gas turbine, so to speak. And this really becomes a jet engine when you add that nozzle to it. So the nozzle takes the air that just got expanded through the turbine, and expands it a little more, and creates a jet of air. And this jet has an associated kinetic energy and momentum with it. And this momentum is what, by reaction force, is what moves your aircraft or your missile forward. But obviously in this case, that's not what we're after. So the air is deflected into another turbine. This is the free turbine. I believe the first one's called the power turbine. This is the free turbine. And the free turbine is connected by a shaft to a alternator. And the alternator takes the rotational mechanical energy and makes it into electric power. All right, so like I mentioned before, compressor, combustion chamber, and turbine make up the gas turbine. And since the working fluid is air, it is called the Brayton cycle. What's going on here is a couple of isentropic processes and a couple at constant pressure. The compressor and the first turbine are the ones that, ideally speaking, are isentropic, and the combustion happens at a constant pressure, heat efficient. And we have a schematic displaying that on the far right, schematic of the electrical generator component. So now a little more on the Brayton cycle. We have a couple of PV and TS diagrams, like I mentioned before, 2 isentropic processes, and 2 at constant pressure, heat addition and heat rejection. But obviously, due to real life irreversibilities, friction, etc., this is not the case. So on the right here, we have an illustration to see the differences between ideal and real. So due to the second law, the entropy is going to go up from 1 to 2, which is the compressor, and it's also going to go up from 3 to 4, the first turbine. You also see that from 2 to 3, it does not quite follow the isobar. We lose a little bit of pressure due to irreversibilities. All right, so like I said before, this apparatus has a lot of built-in pressures, sensors, temperature sensors, probes, all that. So we can get pressure and temperature at the inlet and exit of the compressor. Similarly with the first and second turbine. It does not say here that we need the inlet, or we can get the inlet conditions of the second turbine. That's because it corresponds to the exit temperature and pressure of the first turbine. So a couple more things. Fuel is injected in the combustion chamber. We have that pressure. We also get a couple of electronic values, voltage and current. And lastly, the speed of the generator and the engine, the angular speed rather. The engine, that refers to the compressor and first turbine. They're connected by a shaft. I forgot to mention earlier. That shaft is air so that the power turbine can power the compressor. And then the generator, that's the speed of the second turbine connected to the alternator. All right, so lastly, we can wrap up with some analysis. Like I mentioned before, we get a lot of data. We can take this data along with air tables or necessary equations like the ideal gas law or reverse law, and we can pretty much get whatever we like. We can go get specific enthalpies from tables, use this to compare real and isentropic cases to get efficiencies. You can also get the thermodynamic efficiency of the entire cycle, the rate cycle. And with that, that's all I got.
Go slides.